This is the PowerPoint for the AMS Weather Studies course at Mohawk Valley Community College, WE 101. This will be Chapter 7, where we'll talk about clouds, precipitation, and weather radar. One of the more important questions that this particular chapter will discuss are how clouds form and how does precipitation form. We're going to talk about this as well as weather radar and various methods for measuring precipitation. I'm sure at some point you have seen things called contrails, these bright white streamers of ice crystals that form in the exhaust of a jet aircraft flying in relatively low temperature environments. These generally occur at high altitudes, above 30,000 feet or so. And they can, interestingly enough, modify the cloud cover along very heavily traveled air corridors, for instance along the East Coast, with the possibility of that as much as 5% of the sky in some major flight corridors can be related to basically contrails. Contrails are short for condensation trails, and it's much like the process that occurs when you see your breath in a cold environment as you exhale. If you look in the lower diagram, you can see a number of contrails that are found just south of Chicago here, probably going into O'Hare Field from the south, but you can see the number of contrails and how extensive they are. In terms of cloud formation, we have to talk about water and water vapor, and we know that water vapor is an invisible component of air, but its condensation and deposition products, that is water droplets and ice crystals, are visible. A cloud is the visible product of this condensation or the deposition of water vapor within the atmosphere. To form clouds, we need to have 100% relative humidity. And interestingly enough, in some cloud chambers where we do experiments relative to cloud formation, even at air above 100%, we don't find clouds that will form. The only way in a relatively clean environment that clouds will form is to have the air supersaturated, and even with that, it has to be hundreds of percent above what we would normally find in the atmosphere for cloud formation. So what's going on here? It seems that droplets cannot form in a cloud chamber without a supersaturated environment because of something called the curvature effect. And this curvature effect basically is related to the curvature of the surface of a spherical water droplet. And this radius increases as the radius of the droplet increases. That is, the surface of a small droplet has a greater curvature than the surface of a large droplet. This seems to affect the strength of the bonds between water molecules and also the vaporization pressures and a variety of other chemical factors associated with the water. The bottom line is that in clean air, water vapor will not condense into tiny water droplets unless the air is supersaturated to very high levels. In the real atmosphere, the relative humidity never even approaches these supersaturation values, so tiny droplets would not form or grow. So what makes cloud formation possible? This next slide gives you some details about the size of water droplets and the relative humidity needed for cloud formation. But again, what makes this happen in nature, because there's never the 340% relative humidity associated in the atmosphere. In the atmosphere, we know that clouds form when the relative humidity is close to 100%. And the reason they do so is because of things called nuclei, which are solid or liquid particles that are suspended naturally in the air environment. These condensation nuclei are essential for cloud formation and are abundant in the atmosphere and are continually recycled into the atmosphere from the Earth's surface. Cloud formation may cover anywhere from 60 to 70% of the Earth's atmosphere in any particular day. Here's an example of a day in October 2009, and you can see that the dark blue areas are little cloud coverage, and the whiter areas are where clouds are formed, and they cover a great deal of the surface of the Earth. There are different types of nuclei that we find in the atmosphere. One is called a condensation nuclei, or CCN, cloud condensation nuclei, which promotes condensation of water vapor at temperatures above and below the freezing point of water. Ice-forming nuclei, or IN, are much less common than the CCN, and on most promote formation of ice crystals only at temperatures well below freezing. Hygroscopic nuclei are a special category of nuclei, condensation nuclei, and they have a special attraction for water molecules because they're composed of magnesium chloride, a salt in sea spray that can promote condensation at a relatively low percentage, even as low as 70%. Interestingly enough, urban and industrial areas have many sources of hygroscopic nuclei, and this helps to explain why localities downwind of large cities tend to become somewhat cloudier and rainier than the upwind localities of these same cities. In the late 1700s or so, it was demonstrated that supercooling of water, that is, water cooled below normal freezing point, was possible. And later in that century, it was confirmed the existence of supercooled droplets in the free atmosphere. The question is, how can cloud droplets remain liquid even at temperatures well below freezing? Freezing of fresh water begins with the linking of water molecules to form tiny structures known as ice embryos. It seems that within the very small droplets composing clouds, kinetic molecular activity is sufficient to inhibit growth of these ice embryos to a critical size so that water droplets remain liquid even at temperatures well below freezing. The formation of ice embryos of critical size to the chance of aggregation of water molecules is known as homogeneous or spontaneous nucleation. We know that a cloud droplet can cool as low as about 39 degrees centigrade without freezing, but any additional cooling always leads to homogeneous nucleation. This threshold temperature is called the Schaefer point, who was a pioneer, Vincent J. Schaefer, in physics research at General Electric Laboratory in Schenectady. If the supercooled water droplet contains or somehow comes in contact with foreign particles, the ice-forming nuclei that we talked about earlier, the cloud droplet will freeze at a temperature below the freezing point but well above the Schaefer point. The foreign particle forms what is known as the ice embryo. The growth of the embryo causes the droplet to freeze, and this process is referred to heterogeneous nucleation. Moving from cloud formation now to cloud classification, you can appreciate that clouds come in an infinite variety of shapes and sizes, and if you've ever watched the sky for any period of time, you'll appreciate that fact. As Table 7.1 shows, clouds are classified on the basis of several things, including general appearance or texture as observed from the ground, altitude of the cloud base, the temperature, or the composition of the cloud. If we look at the general appearance, we can find that clouds really only have three basic shapes. They're cirriform, which means they are wispy or fibrous. They are stratiform, which means they are layered, or they're cumuliform, which means puffy or heaped. If you look at Table 7.2, you'll see that these terms that we've used here in terms of general appearance are associated with cloud groups and names of these particular clouds, which give us the specifics for cloud classification that we have listed here. In terms of altitude, we have clouds that are high clouds, clouds that are middle clouds, and low clouds, and clouds with significant vertical development. And each of these have an altitude base and specific meters that are listed here. So you can see basically these cloud groups are very, very specifically designed, and there are approximately 10 different cloud classification groups. Clouds can also be classified as warm or cold. The temperature in a warm cloud is generally greater than 32 degrees Fahrenheit or 0 degrees centigrade, whereas the temperature in a cold cloud is less than those temperatures. Because the average air temperature decreases from sea level through the troposphere to the tropopause, an ascending cloud, air expands and cools. High clouds are therefore colder than lower clouds, and vertically developed clouds that surge to great altitudes, such as thunderstorms or cumulonimbus clouds, may be warm near the base but are generally very cold aloft. Here's some characteristics associated with high cloud classification, and you should kind of get these in your head, that they're high, they're cold, and they have a fibrous appearance. And so if you see clouds that look like this, they are called cirrus, or have the prefix cirro somewhere in their name. Middle clouds tend to be lower, they tend to be warmer, and they can be composed of supercooled water droplets, of mixture of droplets and ice crystals also. The names include the prefix alto, and altostratus and altocumulus are two relatively common cloud types you will associate with these middle clouds. Low clouds reach from the base of the Earth's surface, which we call fog, to a little bit over a mile high. The average temperatures are warmer than the other two cloud types talks about, and is composed primarily of water droplets. Clouds having significant vertical development form in the updrafts of convection currents that can surge to great altitudes in the troposphere, upwards of 10 to 12 miles in some cases. The altitude at which condensation begins to occur through convection is known as the convective condensation level. There are also some interesting and unusual cloud formations as described in the next 3 or 4 slides. I won't take the time here to go over each of them. They're fairly self-explanatory, so take a minute and look at these and understand how these particular cloud types are formed and what makes them unique. Fog is defined as a visibly restricting suspension of tiny water droplets or even ice crystals, which we call ice fog, in an air layer next to the Earth's surface. Fog is a cloud in contact with the ground. Maybe an easier way to define this particular phenomena. With clear night skies, relatively light winds, and an air mass that is humid near the ground and relatively dry aloft, something called radiational cooling may occur, and this causes the air near the ground to approach saturation. This is known as radiational fog or radiation fog. Radiation fog tends to be most common over marshy areas or areas where the soil has been saturated by recent rainfall or even snowmelt. Air that has been chilled by radiational cooling is relatively dense and in hilly terrain drains downslope and settles in lower lying areas such as river valleys and wetlands. We can see that in this area of New York, down in the southern tier in the Catskill region, and over here towards the western part of lower New York State. Fog sometimes accompanies air mass advection. Remember, as an air mass moves from one place to another, which is termed air mass advection, those characteristics change, partly because of the modifying influences of the surfaces over which the air mass travels. When the advecting air passes over a relatively cold surface, the air mass may be chilled to saturation in its lowest levels. This type of cooling is known as advective cooling and occurs, for example, in early spring in the northern states, when mild, humid air may flow over relatively cold or even snow-covered ground. Snow on the ground may chill the overlying air to a dew point, and the fog develops. Fog formed by this advective cooling is known as advection fog. Steam fog, sometimes known as Arctic sea smoke, is fog that develops in the late fall or winter when extremely cold and dry air flows over a large, unfrozen body of water, as seen here. Fog also may develop on hillsides or mountain slopes as a consequence of the upslope movement of humid air. Ascending humid air undergoes expansional cooling as it moves in this direction and eventually reaches saturation. Any further ascent of the saturated air produces something called upslope fog. Let's talk for a minute now about precipitation processes. Clouds are no guarantee that it will rain or snow. In fact, most clouds do not yield any significant rain or snow, as you appreciate. This is because a special combination of circumstances is required for this thing known as precipitation to develop. Precipitation is water in solid or liquid form that falls from clouds to Earth's surface under the influence of gravity. And the key to understanding the mechanisms of precipitation and its formation is the concept of terminal velocity, or the speed of a falling particle. This thing called terminal velocity is the constant speed attained by a particle falling through a motionless fluid such as water or air. The speed of the falling cloud droplet, or ice crystal in some cases, is calm air that is regulated by gravity, the force that accelerates a particle directly downward, or the opposition component of this is the resistance offered by air through which the particle is falling. Because the downward accelerating particle meets increasing air resistance while gravity remains constant, ultimately there is a situation that develops where the two opposing forces come into balance. This terminal velocity helps to explain why the tiny particles that compose clouds don't fall to the earth as precipitation unless they undergo fairly considerable growth. For clouds to precipitate, then, cloud particles must grow large enough that their terminal velocities overwhelm the air resistance that is keeping them from falling. There seems to be two basic methods to increase cloud particles to a size where they can actually achieve terminal velocity, and they are collision coalescence, which are found in warm clouds, and Bergeron-Feindesen process, which is a component of cold clouds. The next 4 slides or so give you some idea about these various processes, so take a minute and look these over. They're fairly self-explanatory, so I won't take time going over them at this point, but these 4 slides help you appreciate the 2 different processes associated with precipitation. Regardless of the mechanisms of formation, once a falling raindrop or even snowflake leaves the base of a cloud, it enters unsaturated air and thus begins to vaporize. The longer the distance to the Earth's surface, that is, the higher the cloud base, and the lower the relative humidity of air beneath the clouds, the greater is the quantity of rain or snow that vaporizes. This is one of the reasons why highlands, being closer to the base of clouds, usually receives more precipitation than lowlands do. It's important for us to understand the different forms of precipitation within the atmosphere. Rain consists of liquid water drops that fall mostly from nimbostratus or cumulonimbus clouds. This slide gives you some of the characteristics associated with rain and forms of rain that we are familiar with. Being from central New York, we're certainly familiar with this stuff called snow, which is an agglomeration of ice crystals in the form of flakes that fall from clouds through the atmosphere to the Earth's surface. Snowflakes have an extreme variety of shapes and sizes, and they can be single crystals, but commonly are conglomerations, and crystals that are shown here may be some of the crystals that you would find if you collected them and looked at them through a microscope. Keep in mind, these snowflakes are not frozen raindrops. They have very distinct shapes and can be classified in a number of different ways based on their altitude from which they were released and the temperature associated with those altitudes. Snow pellets and snow grains are related to snowflakes. Snow pellets, which are called soft hail or graupel, are conical shaped and spherical particles of ice having diameters of 2 to 5 millimeters. Snow grains, which we also know as granular snow, are flat or elongated opaque white particles of ice, usually less than 1 millimeter in diameter, that originate in much the same way as drizzle, except they freeze prior to reaching the ground. This diagram is a schematic cross-section of the lower atmosphere showing temperature conditions for formation of frozen, freezing, and liquid forms that we are familiar with. Freezing rain or freezing drizzle consists of rain drops that become supercooled and at least partially freeze on contact with cold surfaces to form a coating of ice, which we call glaze, on roads, tree branches, and various. This is kind of a modified Stuve diagram, and these are soundings of temperature and dew points indicating conditions that are favorable for freezing rain. Somewhere around 750 to 900 millibars, which is somewhere around 10,000 feet or so, the frozen precipitation particles melt become supercooled as they drop below the 900 millibar area and freeze onto ground surfaces, and we can see that taking place as the precipitation drops. Hail consists of balls or jagged lumps of ice, often characterized by concentric internal layerings resembling the structure of an onion, and this layering is related to the various moisture collection environments that the hail encountered as it formed. Hail forms with intense thunderstorm, generally cumulonimbus clouds characterized by updrafts, very strong updrafts, an abundant supply of supercooled water droplets, and a lot of vertical cloud development. Updrafts transport ice pellets into the middle and upper portions of this cloud, and along the way the ice pellets grow by collecting supercooled water droplets and eventually become too heavy to be supported by these updrafts. The pellets descend through the cloud, exit the cloud base, and enter the air, typically above the freezing point. Pellets begin melting, but they are large enough they will survive the journey to the Earth's surface as hailstones. We know that cloud particles and precipitation are slightly acidic, that is, they're below 7.0 on the pH scale, and they naturally dissolve some atmospheric carbon dioxide and produce a weak carbonic acid, or H2CO3. Acid deposition refers to the delivery of acidic particles, usually sulfuric acid or nitric acid, to the Earth's surface. With acid deposition, a distinction is made between dry and wet deposition. With dry deposition, particulates and gases gravitationally settle on the ground in dry form and then react with water, that is, dew or frost, something of that nature, which increases the acidity of the solution. With wet deposition, airborne particles participate in a complex set of chemical reactions that involve sunlight, water vapor, and other gases, converting to tiny droplets of dilute sulfuric acid and nitric acid the rain droplets that we find in the atmosphere. These acidic particles affect atmospheric chemistry by slowly settling to the Earth's surface, adhering to cloud particles or fog droplets, which we call acid fog, or acting as cloud condensation nuclei. Should precipitation develop, acids dissolve in the precipitation or are swept up by it, increasing the acidity possibly by 200 times or more than normal. The normal pH of rainwater saturated with carbon dioxide is about 5.6 on the pH scale. With pH going below this value, sometimes as low as 4 in some areas, acid rain and fog has been implicated, along with other pollutants, in the decline and dieback of coniferous forests in West Germany and in the Appalachian Mountains from North Carolina to New England, as well as our own Adirondack Mountains. It is found in the Adirondacks that any lake above 2,000 feet or so has been so affected by pH that there are no living organisms found in the vast majority of those water environments in the Adirondack Mountains to date. In terms of affecting forests, acid rain leaches minerals, primarily calcium and potassium, from the soil, decreasing nutrients necessary for plant growth. The change in acidity in the soil also mobilizes some elements which are harmful substitutes for the replacements of calcium and others which the trees can absorb, and this causes a problem in terms of growth of trees in these acid rain environments. This series of slides deals with weather radar. The process in locating precipitation is very important to determining weather in a specific area. Radar stands for radio detection and ranging, and the radar emits microwave signals and receives signals from its target as the beam continually scans large volumes of the lower atmosphere. Today there are approximately 186 of the newly advanced WSR-88D weather radar units monitoring conditions over much of the nation, with most being operated by the National Weather Service and some by the Department of Defense. The radar works as seen here by emitting short pulses of microwave energy, and at these wavelengths radar signals are reflected, or we should really say scattered, by rain, snow, hail, but not by the tiny water particles or ice crystals that are composed of clouds. So this weather radar is designed to detect precipitation-sized particles, but not parent cloud particles. Falling precipitation particles reflect some of the radar signal back to the receiving unit, where it is electronically processed and displayed as it is detected on a computer screen as something known as a radar echo. Today's radar works in both velocity and reflective modes. In the velocity mode, the radar system utilizes the Doppler effect to determine horizontal air motions within a weather system based upon the detected motions of the precipitation particles assumed to be the tracers of the wind. The Doppler effect refers to a shift in the frequency of sound waves or electromagnetic waves, in the case of our radar, emanating from a moving source. For example, the pitch or frequency of a train whistle sounds higher as a train approaches and drops off as a train pulls away. The diagram on the right-hand side of the slide indicates Doppler radar operating in three different weather situations. With a stationary rain shower, the frequency of the return signal is the same as that of the emitted echo. In B, if the rain shower approaches the radar, the frequency of the return echo is greater than that of the emitted signal. And C, if the rain shower moves away from the radar, the frequency of the return echo is less than that of the emitted signal. These frequency shifts can be analyzed and information determined by the information that's received through the radar detection instrument. This sample Doppler weather radar image shows that greens and blues indicate motion toward the radar, whereas reds and yellows, the warmer colors, indicate motion directly away from the radar. Expected to be completed in 2013, the entire fleet of WSR-88D radars is undergoing a major upgrade to dual polarization technology, and this technology provides weather forecasts with more precise information on precipitation type, accumulation, and threat identification, enabling them to more accurately diagnose severe weather. The long-term future of weather radar lies in something known as phased array weather radar, seen here in this figure. This uses multiple beams that are sent out simultaneously, and the entire atmosphere is scanned in 30 seconds instead of the current 5 to 7 minutes, and the radar has the ability to quickly focus on severe weather features such as possible tornadoes. In addition, phased array weather radar provides a more detailed explanation of storm evolution and will help scientists refine conceptual and numerical weather models. In terms of measuring precipitation, rainfall and snowfall are routinely measured in terms of depth of accumulation over a specified interval, usually hourly and every 6 and 24 hours. Measurements are made directly by collecting a volume of rain or snow in a gauge in the next several slides give you some indication about what that gauge looks like and some of the specifics regarding measuring precipitation. Remote sensing is also important, as we described earlier, relative to radar. But radar, besides tracking velocity and other things, also provides estimates of total amount of rainfall. Whereas networks of precipitation gauges measure rainfall at discrete locations, radar measures rainfall with continuous volume scans of the atmosphere centered on the radar site. In addition, satellite sensors are also valuable remote sensing tools for precipitation. Tropical Rainfall Measuring Mission utilizes satellite technology to measure rainfall over areas between latitudes of 40 degrees north and 40 degrees south. Knowledge of tropical rainfall and associated flow of heat energy promises to improve our understanding of the global climate system and make possible the development of more realistic global climate models with more sophisticated technology.